In this video, I will talk about organic electronics-based microspectrometers. First of all, I would like to give an introduction to NSENORICS. NSENORICS was founded in 2017 as a spin-off from the Technische Universität Dresden, with a mission to reveal the world of material sensing. We develop chip-size, miniaturized spectrometers, which are based on organic electronics technologies. With this technology, we can offer much lower cost for material sensing devices compared to traditional solutions and serve various markets, starting from food over textiles, but also many others. In the multiple project, different applications are addressed, from steel manufacturing over woodworking to food industry. The aim is to improve the processes by detecting and analyzing the process data using spectroscopic systems, mainly hyperspectral imaging techniques. Hyperspectral imaging is really a powerful tool for process analysis, but it also comes at high cost, and that can hinder its application. In some cases, the problem might be addressed with much less complexity and also at lower cost. For example, here in multiple, our partner Jotis wants to analyze processing parameters of liquid chocolate during the production process. The use case is described in another tutorial, but the core issue is that it can be solved with much less complexity, which I will explain on the next slide. So in this slide here, I will show the motivation for our technology in the multiple project. The main issues I will show with this matrix. So what do I mean with complexity? In this case, so when we look at the liquid chocolate, imaging is not necessary. So we can already reduce the sensor from an imaging sensor to a point sensor. Similarly, we can also reduce the amount of spectral bands, as in most cases, the analysis of 16 bands is still enough to satisfy the requirements. And typically in hyperspectral imaging, much more than 16 spectral bands are used. Still, the reduction of complexity will not only reduce the cost as much as possible, but we also need to shift the technology from standard semiconductor, which is mostly INGAS, if we talk about the sphere band, to organic electronics technology. And if we do all this complexity and cost reduction, we'll have a lot of benefits. We'll simplify the chip design, we'll have a low amount of data, which also means simplified data analysis. And by moving to organic electronics technology, we can simplify the manufacturing and also have high scalability of the process. For those who have not yet been in contact with organic electronics, I want to have a short glimpse on the technology and its benefits for microspectrometers on the next slide. So here you see the sensor device, which is a multiple thin layer deposited on a substrate. And this thin film deposition is usually done on glass, and the total stack thickness is usually less than 1 micrometer, so you need very little amount of material. It's a highly controlled and scalable process, and you can tune the absorption of the final sensor device using an integrated filter approach. With this approach and with this technology, which is based on organic materials like those shown on the right side, we have access to a wide spectral range, which ranges from the vis down to the sphere range. And the result is such a small spectrometer chip, which you see on the left, which is not more than 1 by 1 centimeter squared. It has 16 separate spectral channels distributed over the sphere range, as you see in the graph. Organic electronics technologies are not completely new. The most prominent related technology are OLEDs, which you might have heard of. And OLED means organic light emitting diodes, which also includes the term organic. The OLED technology has experienced strong upscaling in the last years, and similar effects are also expected for our sensor chips, which will enable the integration in other use cases like those or the one which we specifically addressed here in the multiple project. For the chocolate use case in the multiple project, we integrated our sensor chip in a larger system that allows further integration in a full analysis device. You can see the result in another tutorial of multiple. The integration was done by our project partner, Iris. So in summary, our organic electronics-based microspectrometers allow strong reduction of system complexity for use cases where the ultimate performance of hyperspectral imaging might not be necessary, and comes with a strong reduction of system cost due to its high scalability, similar to the well-known OLED technology. In multiple, this technology is used to analyze the manufacturing parameters of chocolate during the production, which is described in a separate tutorial. Thank you.